Let's move on to lesson 6.1b. We'll be beginning on page 250, the quadrilateral angle sum theorem, theorem 6.1.1. So let's take a look at the figure over on the right. This is a kite. And if you remember from the last lesson, the kite is a four-sided figure, part of the quadrilateral family, and it has two sides that are congruent to each other, KL and ML, and then another two sides that are congruent to each other, KJ and MJ, and that none of these sides have to be parallel. One of the things I can tell you is that their sum of the interior angle measures will equal 360 degrees. So every one of these inside angles, angle K, L, M, and J, add to 360 degrees. This is true for all quadrilaterals. So the inside angles of a square are 360. The inside angles of a rectangle are 360, and so on. One of the ways that they prove this to be true is by drawing a diagonal. In this case, they drew diagonal JL, and if you remember, the diagonal is a line that reaches from one vertice to an opposite vertice. When they draw this diagonal, it creates two triangles, and you can prove that these two triangles add to 180. And if you have two triangles that are 180 degrees, 180 plus 180 equals 360. We have another theorem that will help you solve for these angles, and it's called the convex polygon angle sum theorem. This is theorem 6.1.2. This theorem states that the sum of the inside or interior angle measures of any convex n-gon, in this case we're working with quadrilaterals, is the number of sides minus 2 times 180. So this is a formula for solving for the total sum of the interior angles. So in this case, or in the last case I should say, with the kite, we had four sides, so we would place a 4 where the n is. 4 minus 2 is 2, and 2 times 180 would be 360. So with quadrilaterals you'll have 360, but what if you have more sides? If you have 5 sides or 6 sides, this will help you solve for all of the interior angle measures. On page 252, number 15, it asks us to find the sum of the measures of the interior angles of each convex polygon. So here's an example. Number 15 is finding the sum of the measures of a decagon. Now a decagon has 10 sides. So that's what we know about it. Whenever you're looking at polygons, you'll have to determine how many sides it has. We use the formula we've just learned, and we substitute the 10 sides minus 2, which equals 8, and 8 times 180 equals 1440. Now you might be thinking in your head, wait a minute, we jumped from quadrilaterals to polygons all of a sudden. Well, quadrilaterals are polygons. They're four-sided polygons. So that's what allows us to use this formula. So once again, make sure in your notes you have the sum of the inside angle measures for this formula, because we have another formula coming up. Here's an example of a table that is in your book. It's on page 251. And you can see here we have, if we have a polygon that has 6 sides, which is a hexagon, if we draw diagonals, we see that it is 4 triangles. So 6-sided figure will have 4 triangles, and 4 times 180 is 720. So once again, you see our formula, n for the number of sides. The n minus 2 tells us it would be 4, and 4 times 180 would be 720. In this figure right here, you can see that there are 5 sides. 5 minus 2 is 3. 3 times 180 is 540. Now, we're going to expand on this formula, because not only do we need to know the measure of the angles inside of these polygons, we also need to know what one angle measure is. And this applies only to regular n-gons, or regular polygons, regular quadrilaterals. So this would apply to your square or your rhombus. So to solve for each angle of a regular n-gon, we would use the same formula we used before for the sum, but we will divide by the number of sides. So an example, in your book it's number 17. We're solving for each angle measure of a dodecagon, which is 12 sides. So here is our formula, and we substitute the 12 for n, and 12 minus 2 is 10, times 180 divided by 12. So 10 times 180 divided by 12. 10 times 180 is 1800 divided by 12, and you have 150 degrees. The last theorem in this lesson is theorem 6.1.3. You have exterior angles of n-gon sum theorem. I named that. It's not a great name. Basically what we're doing is using the exterior angles of a quadrilateral to solve a certain property. And let's just take a look at the pictures first. Over to the left we have a quadrilateral, and it's a trapezoid type of a feature. It has 4 sides, and they've extended each side. So if you see that, every time they extend a side, it creates an exterior angle. One of the things that you know is if you take this exterior angle, example 75 degrees, the angle next to it will be 105 degrees, because this is a straight angle and we can subtract from 180 to solve that. If we want to know what the sum of the measures of an external angle from each vertex of this quadrilateral is, so if I say to you, what is the sum of all of the measures that are shown, they add up to 360 degrees. So for any quadrilateral, if you only had the inside measures, you could extend a line, find the angles on the outside, the exterior angles, and you could also solve for those. So if this is 360 degrees, let's see what the next picture tells us. This is a triangle, and it has exterior angle measures of 71, 134, and 155. And if we add those, guess what? They equal 360 degrees. So we can draw a conclusion here. The sum of the exterior angles will equal 360 degrees. This is easy to remember because this is the sum of the interior angles of a square, 360 degrees. It's also the degree measure of a circle, and that's where this eventually goes, is into calculus and solving circles. Now we can take this knowing this fact. If we take a regular figure, in an example to the right here, a pentagon, it has 5 sides. It's regular. It shows you that because each side has 1 hash mark. You can now take the sum of the interior angles from our previous theorem, solve what that total would be, divide it by 5 to find out what each angle measure would be, and then you can subtract from 180. So let me say that again, and let me go back and review something for you. Here's the table. It says with interior angles of a pentagon, the sum of their measure would be 540. It would be 540 using the new formula, 540 divided by 5, so that's 180 divided by 5. Each one of those would be 108 degrees. So if each one of these inside angles was 108, angle 1, angle 2, angle 3, angle 4, and angle 5 would all be 75 degrees. Let's look at the math. The problems 15 and 16 in your book. 15 says find the sum of the measure of the interior angle in each convex polygon. We used the formula for that. It's a decagon with 10 sides. We substitute the 10. 10 minus 2 is 8 times 180 equals 1440. Now number 16 says to find the interior angle measure of each. So we use the same formula, but we divide by the number of sides, and it tells us that in a pentagon, a regular pentagon, the interior angles are 108, and if we look back here, if the interior angles of the pentagon are 108, the exterior angles are 75. Number 19, similar to one of the homework problems in your book, says state another name for each polygon. We're asked to find another name for an equilateral parallelogram. If you remember, a parallelogram has 2 sets of sides that are parallel, but it doesn't have 90-degree angles. It's actually slanted. It usually looks like a rectangle that's slanted. However, they're saying that we should have equilateral side lengths. So that would be our rhombus from this lesson. Number 29, which is similar to one of your problems, says to find the measure of angle P in each polygon. It shows a trapezoid that's similar to this one from the theorem, and it shows the measure of one of the exterior angles. Remember, if you have an exterior angle and you need to find an angle next to it, you'll subtract the exterior angle from 180 degrees. So in this case, it would be 107 from 180. In the case of number 29, it would be 117 from 180. Okay, that's it for this lesson. Go ahead and do your homework and give me a call if you need any assistance.